11.3, the Newton-Raphson method, A2 Pure Maths, chapter 11 is numerical methods. So the Newton-Raphson method is another example of a numerical method. Again, using an iterative formula. So this is the formula that we've got here. So we've got x of n plus 1, and then we've just got xn on this side. So you'll be given a starting point that you substitute in. Notice here that we're using the derivative of f of x, and we're just going to keep applying this formula over and over again to find better approximations. So what is actually happening is we are using the tangent, and we'll prove this method in an example coming up. So we're using the tangent at that point. So we're getting our starting point, finding the tangent, and we are looking for where that tangent crosses the x-axis in order to give an approximation. So just have a look at this example, which is not in the notes, but it's just for you to focus on and try and get your head around what's happening. This is the graph of f of x equals ln x minus 3. So my root is over here. And I am going to start with x1 equals 2, just because it gives us a little bit of something to look at. So there's your tangent. F of x equals 2. You have a tangent, and it's cutting the axis here. So my next tangent is going to be using that x value there. So when you apply the formula the next time, you are applying it to the next tangent, which we can see because this is quite a shallow curve here and we've got quite a low gradient, you can see that this tangent is getting closer to where that root is going to be. If I apply it again, so we cut the x-axis around 14 here. So when I put the next tangent on, so the blue one, which is the tangent here, we're getting closer to our point of intersection. We're hitting the x-axis about 19, so the next tangent is going to be there, and the idea is that you can keep going so that eventually your tangent is intersecting with the curve, which I think it's almost lying on it at that point. So we've got there fairly fast. It wouldn't give us the exact value, I don't think yet. We're just missing it. So the value's coming in here, and when we zoom right in, you can see that my next tangent would be around 20.06. So that's what's happening with the Newton-Raphson method. It doesn't always work. So if we just take these off and we have a look at log graph, let's just transform the log graph up, and instead of starting at 2, I want to start this end. So we're going to start at 9. So I'm going to put the first one on. The problem is, because this gradient here is close to 0, my point of intersection I'm looking for is 1, which you knew already. But actually the tangent has come over here. So, and that's to do with how shallow this gradient is. So it's ended up with a point of intersection over here. So if we were to put the next one on, we're not going to see it, because when I substitute that value, that x value, in, so it's about minus 11, on the log graph, I can't calculate that anyway, and therefore I'm not going to be able to find a solution. So in this case, Newton-Raphson method has failed because I've not been able to get close to that value. So just like the iterative method, not every starting point on the graph is going to find that root. So if you find one that is working, if it is conversion, then the more times you repeat it, then the closer you get to the real root. It might be that just starting in the wrong place on the graph has meant that it's converging very, very slowly, or it might fail completely. So that's what that first section is talking about. So if you want to pause the video and just have a read through it, it might make a little bit of sense, hopefully. I'm going to move on to example 11.3.1. So we've been given this graph. Notice it's a continuous graph. This is the function, so it's x cubed plus 2x squared minus 5x minus 4. And we're looking at this point A here with coordinate P, which is a stationary point on the curve. And we're going to be looking for the root alpha, which is in the interval 1.8 to 1.9. So we've been given all that information in the question. So part A, explain why P is not a suitable starting point. So if we think about what we've just looked at, if we are looking at the tangent at A, the tangent at A, because we've got a stationary point, we know that we've got a horizontal line. That is never going to cross the x-axis. Okay? Therefore, your Newton-Raphson method is going to fail because it is all dependent on the tangents intersecting the x-axis and trying to get closer to that root. Formula would fail because at the tangent the gradient is 0, and if we just have a look at that formula again, which is given to you in the formula book, at this point this is f dashed of that starting point, so the gradient function, if I was to substitute p into f dash, I should be getting 0 because that means we've got a tangent, and I can't divide by 0. Now, in terms of answering that question, that is not a valid answer to the question on why it's not a suitable approximation. You have to comment on the Newton-Raphson process. You can't comment on the formula. So although it is true to say that f dashed of p is equal to 0 and you can't divide by 0, it wouldn't get you any marks. They want you to recognise that you can't. It's not going to intersect the x-axis. Okay. So by using so part B, by using x0 equals 2 as a first approximation to alpha. Just find the pen. We need to apply Newton-Raphson twice. So there's going to be marks for differentiating, so f dashed. Quite a nice derivative here. And then to find x1, using the formula that we've got above, so we're doing x0, which is 2, minus f of x0 over f dashed. Now I would write that in to your working to show that you understand where the formula is coming from and what you're using. So I'm going to use a calculator like we did before. So we press 2 equals to make it go into the answer memory. It is a little bit faffy. So we've got answer minus fraction button. You've got to type all of that in. I probably wouldn't bother doing this if it wanted just one lot of Newton-Raphson process, but because we've been asked to do it twice, it probably is worth doing. It's up to you whether you do it. If you're not going to go through the process of typing all this in, what I would suggest is that you watch out for that minus sign in the middle. So do be careful with that, because so calculate this first and then do 2 minus that. So we've got 28 over 15 as our first value. Notice in the question it is asking for us to give it to 3 significant figures. So x2 is equal to, now if you're not going to use your calculator like I have, and you're going to type this in again, you have to use that full value. So I might write 1.87 here, but you need to be using 28 over 15, which is what the calculator is going to do, because otherwise you will lose your accuracy on it, and the whole process is working on having that accuracy there. So to 3 significant figures, I get 1.86, which is what it's asked me to do to find an approximation. So that's our approximation for alpha. For part C, by considering the change of sign over an appropriate interval, show that the answer to part B is accurate to 3 significant figures. This is exactly the same as what we were doing previously. So if I'm using 1.86, I'm going to do f of 1.855, which is equal to minus 9.85. And I'm going to do f of 1.865, which is equal to 0.118. So I'm using f of x that was given in the question there, just substituting those in. The upper bound on 1.86, the lower bound on 1.86. There we are, we've still got the conclusion saved. So as f of x is continuous, there is a change of sign in the interval, and this time our interval is 1.855, 1.855. Conclusion would be 1.86 is correct. 2, 3 significant numbers. And that's the end of that example.